measuring what you've made. Now you've made something and you want it to perform in the field, and you want to understand how its performance changes as it's used. And so one of the most frustrating things about electrochemical energy storage devices, aside from the fact that they don't have quite enough charge, right? You're running out of battery at the end of the day, is that the batteries also wear out. Right? And so we want to understand that technically. This is a really nice image made by Christoph Berkel that summarizes the various ways that batteries can wear out. In this case, if you look at this, you have on the left side, you have the anode, on the right side you have the cathode. You have going from outside in, you have current collectors. On the left it's copper, on the right it's aluminum. On the left side, on the anode side, you have a carbon material, typically, that is attached to the copper current collector with something called a binder. And over time, that copper can do a number of different things. It can deposit, it can kind of get out into the electrolyte, it can deposit, it can form its own dendrites. And I don't know if you know what dendrites are. They're drawn here sort of in a cartoonish way, but they are high aspect ratio slivers of a material, and if they get in the wrong place, they could actually cause a short. As it's drawn here for the copper, it's not drawn as a debilitating short, but the other ones are, and we'll get to those. Other things that can happen is that your material, your anode material, your carbon, can break down, and as it breaks down, as it cracks, as it decrepitates, it loses contact, and losing contact means, physical contact means that you have poorer electrical contact and your resistance will go up in your cell. It could also, there's a layer in batteries called the SEI layer. Dr. Gupta talked about that a little bit before, and that, that layer can change and grow over time, which also can cause an increase in the resistance. It also can cause some irreversible reactions, and whenever you have a battery, you want to have only reversible reactions. Okay? But what also can happen is that the ions, in this case, think about lithium ions, they are supposed to go into the carbon on the left, the anode side. But sometimes they build up locally. You could imagine they might build up locally because of some sort of electrical phenomenon that enhances the electric field, and they form dendrites. Those dendrites will tend to grow back toward the cathode, so from left to right. When that happens, if it reaches the other side, so if that yellow dendrite in this figure reaches the other electrode, then you immediately have a short. And that short, when you're trying to drive a load, will cause a channeling of the current, and high current over a fairly resistive layer causes a lot of heating. That heating, in turn, will cause your device to fail. It might even catch on fire. Okay? Similar things can happen with with the right side, the cathode material. The cathode materials are typically made with transition metals, so think of cobalt. And so a similar dendritic formation can happen. Generally, you have a separator between the two, the anode and the cathode, and that should suppress the growth of dendrites, but it doesn't always work that way. The dendrites can penetrate through. On the right side, on the cathode side, that material over time, over many cycles, it will be growing and shrinking as it changes chemically. And as it grows and shrinks, there are stresses induced. Those stresses can cause fracture, local fracture, and again, the same kind of thing can happen where the material loses electrical contact with the rest, and so the resistance will go up, which is not necessarily a debilitating failure, but it's just a slow degradation of performance. So comparing supercapacitors and batteries, or another word for supercapacitor is ultracapacitor. This is another spider chart made by Maxwell, which is a company that makes supercapacitors or ultracapacitors, and you look at many of the dimensions shown here, and on most things, if you look at the left side, the ultracapacitors have very, very good performance in terms of environmental safety, recycling, high temperature range compared to these other batteries. The three other batteries that are shown here are lead acid, nickel metal hydride, and lithium ion. On the right side, you'll see that some of the places where ultracapacitors don't perform as well, and we've covered these, right? So self-discharge is a big problem. Batteries hold their charge better than capacitors do. Cyclic stability, though, is an exception. Obviously, we've talked about this, and we'll talk more. The supercapacitors have much, much better cycling stability. Energy density, though, is the one that is the place where ultracapacitors or supercapacitors fall short, as well as cost, right? So if you look at the energy cost says that supercapacitors are not very inexpensive. So they're expensive on an energy basis, but on a power basis, and we know this from all the things we've learned, they're still very good on cost and overall power as well. So this slide kind of says what we said before. I just wanted to point out here on batteries, if you look at what happens with a battery as temperature increases, and we'll have an entire lecture later today on temperature effects in supercapacitors, but for batteries, similar types of things happen. If you look at, if you store a battery over a period of years, or a good fraction of a year at certain temperatures, its internal resistance will go up. And what's happening here is that there are some reactions that are occurring that are changing the electrolyte, that are causing interference pathways with the flow of charge inside the device. Here's another view of electrode aging in batteries, just to give a bit of a close-up shot. Generally speaking, on the carbon side, you have graphitized carbon, and so it has layers of graphene. And you can kind of peel back those layers. What you want to see is just single ions, lithium ions typically, that are going into the carbon, and they intercalate between the graphene layers. That's the little red dots that have gone in between the graphene layers. But if you get some of your solvent or SEI layer into that space between layers, right, then it can start to peel up the layers, and it can exfoliate the graphene away from its neighbors, and that can cause a permanent effect and a permanent failure. Okay. On the cathode side, we have similar general effects, but in essence what happens is you're corroding your material and your binder. The binder is the material that keeps all these kind of particles together and allows charge to flow. And this binder can decompose, and when the binder decomposes and the electrolyte decomposes, you can get some gas evolution. So if you have a sealed package, then you can start to build up pressure. And I think that you can all imagine that building up pressure inside of a device that contains lithium, which when exposed to air can combust, right? That's not a very good situation, and that's why people think of lithium-ion batteries as generally more dangerous than other kinds of batteries. So obviously we also wouldn't want to have something like lead. Lead acid batteries usually are not tightly sealed, so that if there is some gas release, the gas can escape. But if it couldn't, then you'd also have problems there with contamination, with toxic contamination. So looking again at supercapacitors, I'm kind of going back and forth talking about batteries and supercapacitors. Supercapacitors or ultracapacitors typically do not have a clearly defined end of life, because it's just often a slow degradation in performance. And we're going to see examples of that as we go through. You end up, if you want to know whether your supercapacitor is how old it is, then you would just look for a general drifting downward in capacitance and upward in resistance. So when you do your electrochemical impedance spectroscopy, like Kieran showed us yesterday in the lab, you would be looking for changes in the resistances that you see there. And then for capacitance, we'd be looking for doing a CV curve or a charge discharge test for that. But generally speaking, there's no clear definition of the end of life because it depends on your application. Usually a supercapacitor will be overrated for the application so that it has some bandwidth to decay in performance a bit before the rest of your system is affected. Here's just a quote from a book on ultracapacitor aging. The origin is, there's many different phenomena. So I know that most of you in the audience are scientists. There are plenty of engineers too. But even the scientists should be looking at this and saying, you know, what among these complicated factors for aging, what's happening chemically? For example, if you're a chemistry person, if you're a chemistry major, what's happening chemically? And is there a way, by understanding what's happening chemically, is there a way to counteract it? Could you, for example, change your electrolyte so that it was more stable, or put an additive into your electrolyte that would counteract some sort of a adverse reaction? Generally speaking, when you open a capacitor after it's been aged, you'll see oxidation on the separator, a brown coloration. So that's an example. As you're making samples in the lab and testing them, if you start to see a brown coloration of your separator, that's that film that sits between your cathode and anode, then you'd expect that some oxidation was happening and that the performance was going down. We've seen this a little bit, so just to make it clear, you can run a frequency test and show that your capacitance, as you go to very, very high frequencies, your capacitance or effective capacitance is going down to zero. Your series resistance as well will decrease with frequency. And these are the kinds of things that you would be tracking over time. You could run a test such as this one. If you look at temperature dependence, in this case, this is a test of a particular supercapacitor with an organic electrolyte, and you have a variation in capacitance and ESR, equivalent series resistance, with temperature. And actually, in this case, they both get better, right? Your series resistance, or excuse me, the series resistance drops, which is something that you want. The capacitance slightly increases. So in this case, it's not such a problem, but you'd want to be watching this over a number of cycles, or with a duration of time. This is another example, an effective temperature, and we'll talk more about temperature effects in the next lecture, but just to give you a bit of a preview, if you look at self-discharge as a function of temperature, I think that this is mostly intuitive to the audience, where you would say if temperature increases and there's some sort of leakage that happens, that it will be stronger. The leakage will be higher as temperature increases, and indeed we see that here. In fact, in a very, very strong way. If you look at the percent of charge, when it's very cold, things are stable. And when it's very hot, you see a very strong decay. Although I would say in this case, this is a pretty good capacitor, right? At 65 degrees C, it's only losing half of its charge in 20 days. And 65 degrees C is really hot, right? That's if you're taking your device, leaving it in your car in Jodhpur in May, right, with the windows up, maybe it would be 65, right? Cyclic stability is another factor here that is important. The capacitance drops over cycles, but look at the number of cycles here. This is for a particular Maxwell device. It's at room temperature. it's being cycled between a little bit more than 1 volt and a little over 2 volts with 90 amps, constant current cycling. And you can see that it's after 100,000 cycles, you've only lost 10% of your performance. That's impressive. That's impressive. The equivalent series resistance has drifted up just a little bit, but nothing significant there. And then another type of testing that people do is DC testing, in which you would just take a device and keep it at a certain voltage. So you would force it to stay at a certain voltage. And then what's happening here, you see individual points on these curves. At those points, you're taking it out and you're doing a CV scan or you're doing an EIS to find the equivalent series resistance. And you put it back into constant voltage testing. And in this case, you can see that when you keep your device at a constant voltage, here you have the resistance increasing significantly upon charging and discharging, so that you're measuring that in those cases, and your capacitance decreases, but still not bad. I mean, it takes many thousands of hours to see a degradation of 10 to 15% in your capacitance. Your resistance goes up by significantly more than that.